Hello, in this video we'll explore some more features of the PSIM using the half-wave rectifier circuit. We have created this circuit in our previous video. We added a sinusoidal source having 110 volt peak. Then we have the 10 ohm load resistor and we have an ideal diode. We added two probes, one at the source and one at the load side. And from here we can run the PSIM simulation. The other alternate option is simulate, and then from the simulate menu you can go to the run PSIM simulation. So we'll use this shortcut, run the PSIM simulation. And when the simulation is done, it gives you an option to select the available variable. The voltages are currents that are available for measurement, and you can click and add them and it will display the result. I want to introduce the simulation control here. From the simulate menu you can add the simulation control. Just place it in the editor window, and these are the options. When you double click this control, these are the options that appears. Among these, the important parameter is the simulation time. So if I use, for instance, 0.01, so my simulation will run for 0.01 seconds. And I just want to show you by running this simulation. Just have a look that it's almost a bit more than a half a cycle. And now I want to double click and reduce it to 0.1 seconds. Let's simulate this again. And now if I add this waveform, you can see that there are 1, 2, 3, 4, 5, 6, almost 6 cycles. So you can see that how we can control the simulation time just by using this simulation control and go to the total time. The other important parameter is the time step, and this will come handy when we deal with high frequency. So for the moment we'll leave it as it is, but when we go to the domain of DC to DC converters or inverters, they will have time step as the vital parameter. Now the next thing I want to show you is that when we simulate, we add the variables. They appear in the very same window. They are kind of overlapped. So if you want to have multiple axes to have a separate plot of V in and V out, we can do that as well. Let me simulate and let me cancel this option. At the moment we have a single axis, and if we want to assign a wave, we can just double click and we can select the one. But there is another option that we want to explore. It says split window, and here are different options. For instance, the first number represents the number of rows, the second the number of columns. So I want a 2 by 1 because we have two waveforms here, the source voltage and the load voltage. Now if I double click the first one, I can add V in, and you can see that only the waveform is appeared in the upper axis, and now double click the lower axis and add V out. And if I zoom in, you can see that the source voltage looks like this, a sinusoidal waveform, and here is the half wave rectified output waveform. So using these controls, we can have a better visibility of our output and input. Another thing that I want to mention here is that the probes that I have added was this one. As you can see, this has only one terminal, and because this voltage is measured with respect to the ground. So in upcoming videos where we need voltage measurement with respect to some other reference, some reference other than ground, for instance, if I want to measure the voltage of the diode, then I'll use this particular option, having two terminals, and we'll connect one of the terminal over here and the other terminal over here to the cathode, and this will gives us the diode voltage. So I'll just type in VD and I can simulate it again, and you can see that now we have VD in addition to V in and V out. So I'll just cancel and I'll come to the split option, and this time I'll select 3 cross 1, and I'll add say V in here, and okay, and then I'll add the VD over here, press OK, and finally I'll add V out. So here are our three waveforms: the V in, VD and V out, the voltage, the source voltage, the diode voltage, and the load voltage. And based on these waveforms, we can perform several analysis. The analysis includes the FFT, the average voltage, or maybe current, the RMS. We can find the power factor, the THD. To do that, we can enable the cursor lines. So here in the bottom, remember we are operating in the SimView, that is the waveform viewer, and in the background we have, here in the background we have the editor window. So keep it in mind that we are operating in the SimView, that is the waveform viewer. So here we can first enable the cursor lines, and we can use these two cursors to select some range, and here we have some measurements. It says that x1, the first cursor, that is at 1.66 10 to the power negative 2, and the other one is at 3.33 10 to the power negative 2. So the difference between these two is 1.66 or 67 10 to the power negative 2. This is the time difference between these two cursor, and so the average is now like 35, and the RMS is like 55. So for THD, we have to set the fundamental frequency. So